Hello, everyone, and welcome back to Thermo Shorts. So far in the class, we've been talking only about closed systems. We have a process or a flow chart that I'm showing here for how to solve those problems. But in today's lecture and for the next module of this class, we'll be thinking about open systems. Now, before we can figure out what's happening with the energy in a closed system, first, we need to know how to account for what happens to the mass. So when we're doing an open system problem, the general things we'll need to do are understand where we can draw our control volume. So how do we separate the system from the surroundings? Then we'll answer the question, what happens to the mass? And once we know that, then we can answer the question, what happens to the energy? Today's lecture, we'll talk about what happens to the mass. Here, we have a verbal description and an equation for conservation of mass. Sometimes we call this equation the continuity equation. And basically, what it says is that the change in mass in my system over time is equal to all the mass I add minus all the mass I take away. Now, this is probably not surprising to you, although you may not have seen it formally in an equation like this. So here's kind of a sketch of what this might look like. Here I have maybe a ductwork system with one inlet and two outlets. What this equation says is that the amount of mass in my system at the end of the time I'm looking at minus the initial mass can be found by adding up all the mass I put in and subtracting all the mass I take out. We also have this special condition that we call steady state. So when we have a system that's at steady state, that means all the parameters in our system are constant with time. So nothing is changing as time moves forward. And since the amount of mass in our system is a property of our system, then if it's not changing with time, then M2 is equal to M1. And what we find is all the mass that we add to the system is equal to all the mass that we take out of the system. When we were talking about closed systems, we would always talk about the elapsed time version of the first law. All the mass stayed inside our system, and we looked at how the energy changed over time. With open systems, we'll often be interested in an instantaneous snapshot of what's going on in our system. So we'll need a rate equation. To get the rate equation for conservation of mass, we take the equation that we've been talking about and we divide all the terms by delta t. Then we take delta t as the limit goes to 0. And what happens then is we see that the rate of change of mass inside our system over time is equal to the sum of the mass flow rates at all our inlets to the system minus the sum of the mass flow rates at the outlets to our system. So when I try to draw this out in a picture, what I see is that the rate of change of mass into my system can be found by adding up all the mass flow rates that are coming in and subtracting all the mass flow rates that go out. Just like with the elapsed time version of this equation, we can also think about what happens at steady state. Now, if the mass is not changing with time because we're at steady state, then the rate of change of the mass in our system is equal to 0. In that case, dm by dt is equal to 0. And then we get to this equation down here that the sum of all the mass flow rates coming into our system is equal to the sum of all the mass flow rates going out of our system. But most of the time in thermodynamics, we'll get to a place like this where we have a governing equation, but maybe we don't know how to treat any of these terms. So if we're at steady state, we can get rid of this term, it becomes 0, but I don't know how to calculate the mass flow rates yet. If you'd like to see how we derive the equation for mass flow rate, you can look at the long version of this lecture. But here, I'm just going to say that this is equal to the average velocity of the flow at a particular inlet or outlet, multiplied by the cross-sectional area at that inlet or outlet, divided by the specific volume of whatever our fluid is at that inlet or outlet. So in the elapsed time version of the first law that we were using for closed systems, we would be fixing states at different times. But in open systems, where we're looking at a snapshot of what's going on in our system, what we'll do is we'll try to fix the state of our fluids at different positions. So either at inlets or at outlets. So I can use this equation if I have enough information to find the mass flow rate at all of my inlets and all of my outlets, and then I put that back into my governing continuity equation. So if I make that substitution here, I go from this equation, but now I can substitute in my equation for mass flow rates, and I get something that looks like this. The rate of change of mass in my system is equal to the velocity times the area divided by the specific volume at all the inlets minus the same at all the outlets. Again, I can have this special case where my system is at steady state, and if my system is at steady state, the sum of all the mass flow rates going into my system is equal to the sum of all the mass flow rates going out of my system. So to maintain that mass as constant in my system, basically I have one in and one out when I'm thinking about the mass. So that concludes the short for today. I'll see you again next time.